ladies and gentlemen. We're taking a look at electronegativity down a group. As a reminder, a group goes down, okay? So that is a group, and a period goes across. So that is a period. Okay, the first thing to do, of course, is to define electronegativity. So electronegativity is usually abbreviated with this sort of strange looking X that comes from the Greek alphabet. And it is defined as attraction for electrons in a bond. So when two atoms are bonded together, the attraction that one atom has for electrons. Now, if you look up the periodic trends data, which you have, then you will see that the highest electronegativity on the chart is there with fluorine, and when we go down to chlorine, it's a little bit less, okay? And then as we go across, hydrogen has quite a low electronegativity. So, so we know that the electronegativity for hydrogen, right, which is 2.2, is a lot less than the electronegativity for fluorine, which is 3.98, according to your charts. Oops, I really don't want to do that. I want to do this to emphasize that. There we go. So, hydrogen is here, has one proton and one electron, and it has an electronegativity of only 2.2. Fluorine, on the other hand, all the way across the table, has got 9 protons and 9 electrons, which I'm putting in here, and it has an electronegativity that is much bigger, 3.98. Okay? And so that is the way that we look at electronegativity. We say fluorine would attract electrons much more than hydrogen. So fluorine attracts electrons more than hydrogen. Okay, so the trends are fairly straightforward. Now let's take a look at the reasons. Okay, so this time we're going to go over to the right, okay, and we're going to say this is fluorine right here, and this is chlorine right here. All right, and we're going to do the same analysis that we've done before. So fluorine has 9 electrons, chlorine has 17. So fluorine will have a positive 9 in the nucleus with 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. Chlorine will have a positive 17 in the nucleus and 17 electrons, which I'm going to go ahead and put in here as quickly as I can. Apologies if you can hear the lawnmower outside. That's my neighbor mowing the lawn. Now, down a group, as we already saw, the trend is that the electronegativity decreases down a group. In a way, electronegativity is kind of the opposite of ionization energy. Ionization energy is how much is required to remove an electron, and electronegativity is how attracted the electron is to the atom. So they kind of go opposite each other. So down a group, the electronegativity decreases. Now, the reason for that, excuse me, is fairly simple. Again, that is a relatively small atomic radius. It's quite close together, and so quite close to the nucleus. And so there is a pretty large attractive force between the nucleus and the outside electrons. And so you have a large attractive force with a small atomic radius. You go down, you add an energy level, and you have a larger distance between the nucleus and the valence electrons. So you have a smaller attractive force with a larger distance between the nucleus and the valence electron. All right, so that's what's going on. So let's put that into English words. All right, so here we've got two energy levels. And here we've got three energy levels. So what we can say is that as the atomic radius increases, which is another way of saying that the valence energy level is further from the nucleus, the attraction for an electron decreases. And that is how electronegativity works down a group.